So I would like to present application of scattering parameters to estimation DPL time lag of the thermal model. So at first, I would like to say about the Fourier-Kirchhoff equation. This equation can be usefully applied to describe the heat transfer in many applications, especially for large structures and for long times. But in case of the small circuits, in case of the nanoelectronics, in case of the mesoscopic systems, this equation will not give correct results. So we would like to analyze why. The first reason is included in the Fourier law equation, in which we have the heat propagation with infinitive speed. So the heat flow from the boundary condition will go to the structure of the heated domain with infinitive speed. The second problem is associated with instantaneous changing of the heat flux and temperature gradient in the same time. So both of these problems are in the Fourier's law and are in the Fourier-Kirchhoff equation. Especially for nanoelectronic structures where we have the size comparable with the 4 nanometers up to, for example, 25 nanometers, we have this problem. For example, for this transistor, which is based from the nanotube, we have the size of the transistor, so it is the size for which the temperature will be go. We have the lattice constants, 5, 12, maybe 20 times smaller than, larger than the size of the transistor. So we cannot use directed Fourier-Kirchhoff based on this phenomena. The next problem is with the Green-Cabuto formalism, in which the thermal conductivity is estimated, is defined using many atoms, for example, 1 million atoms. Another reason is associated with the geometry and the number of the atoms. And for this, we can say that the thermal conductivity can be dependent to the number of the atoms for particular simulation, or can be dependent to the temperature. And additionally, for nanostructures, we will think about the temperature, but generally we have local energy with big deviation of the energy. So we cannot directly treat these results as a real temperature. We have to take it as a approximation of the typical temperature in a particular place. Okay, so for modeling modern processors like Haswell or Broadwell, we should to use not traditional Fourier-Kirchhoff equation, but we should to use Boltzmann transfer equation, or for example, we can use proposed by the Tsu a dual phase-like equation. In this equation, we have two time lags. The first one associated with the heat flux, and the second one associated with the temperature. So using the Taylor expansion, we can write the thermal equation in the new form, in which we have the first and the second time lag, and it is the second form of this equation. This equation can be useful to describe modern processors, for example, in the cell phones. We have many equations which can be used to describe the heat transfer. For example, we can use also Maxwell-Catanov-Vernet equation, which is similar to DPL model, but is simpler. We can also use ballistic conductive heat transfer model, but also the DPL model can be used to modeling the same examples. And we try also apply Grun-van Letnikov differential operators for approximation of the Laplacian and time derivativity. Okay, the DPL equation has been proved experimentally in atomic force microscope, and this equation has been also proved theoretically by Le Bon and Dubois that we can use DPL for approximation of Boltzmann transfer equation with described with or used with radiation. So at first we'll consider monodimensional heat transfer equation, Fourier-Kirchhoff and DPL. And in this equation, we will take into account two time lags. And we have to use the new boundary condition to write correctly Fourier Fourier law. And now we can solve this one-dimensional equation using Laplace transform. And now we'll obtain the final results. So in case of the Fourier-Kirchhoff model, for which time lags are equal to 0, we'll have the following solution. And in case of the DPL, we'll have this solution. So as you see, we have the similar results. But also we have this factor, which is introduced by the boundary condition and it is correct with, it is coherent with the DPL model equation. Now we'll consider the results using amplitudes and using changing in the arguments. And what we can say that for frequencies smaller than 1 gigahertz, the amplitude of DPL and Fourier-Kirchhoff model is quite similar. And it is zoom in, as you see, it is quite similar results. We can also define the equivalent time lag, which will be calculated from the results time shift and from the frequency. And as you see, the delay in the monodimensional model, for example, in the one-dimensional Cartesian DPL model, for about 1 gigahertz or 3 gigahertz have the same delay. So we can say that, for example, for Cooper, we have this delay. For the silicon, we have this delay, plumb, and platinum. Okay, the same solution, but for one-dimensional cylindrical equation, we have quite similar results. And for spherical equation, the one-dimensional spherical equation, we have quite similar results also. And I said about the product which is in the final solution. This product is important for high frequencies, like for this, and can be modeling using special block. I will say that it is the filtering element. So we have the signal delay, we have the Fourier-Kirchhoff model, signal delay, and filtering element. So for frequencies typically up to 1 gigahertz or 1.5 gigahertz, we can, and for the silicon systems, for the thermal simulation using DPL model, we can use Fourier-Kirchhoff model, and we have introduced only the signal delay. And for example, up to 12 gigahertz, we have to take into account also this filtering element. Okay. Now we know that temperature will not change too much, but we can analyze the problem from the point of the impedance of this simulated example. So we'll take into account thermal impedance of this one monodimensional system. We will divide this thermal impedance by thermal impedance of the silicon for 0 frequencies for normalization. So in this axis, we have a thermal resistance. In this axis, we have the thermal capacitance, and we'll change the frequency. So as you see, in case of the one-dimensional Cartesian system, in case of the silicon, the DPL and Fourier-Kirchhoff model will give the same results for small frequency and for increasing the frequency. In case of for the platinum, in case of the silicon, we have the same results for small frequencies, and for higher frequencies, we have different results. Okay, for one-dimensional cylindrical systems, the same. At the beginning, we have the same results. For higher frequencies, we have different results for DPL and Fourier-Kirchhoff for modeling of the thermal impedance. And in case of the silicon, we have different results for higher frequencies. Okay, now this result is for distance 100 nanometers from the centrum of the element. When we decrease this distance, so when we analyze the smaller elements, we'll have this set of the results, the bottom row. And as you see, the Fourier-Kirchhoff is equivalent to DPL only for small frequencies. For higher frequencies, we have different results. The same for silicon. So for and the same for one-dimensional cylindrical system. So Fourier-Kirchhoff can be used only for small frequencies. So as I said, using DPL model, you can use this model to obtain correct results, or we can use simplification of this model using only the delay and this block for simplified calculations. So we can simulate both electric domain and thermal domain from the from the electric domain, we'll get the heat dissipated in the system. We'll transfer it to the thermal domain. In thermal domain, we'll use the signal delay or signal delay, additionally this factor. And we can use traditional Fourier-Kirchhoff model up to 1.5 gigahertz. And the calculated temperature can be transferred to the electric domain to change the parameters of the transistors and other elements. Okay. Now we would like to obtain more precise simulation of the system in which we have more components. In this purpose, we can apply harmonic temperature field. So in case of the regular temperature, we'll use the imaginary temperature. So DPL can be written in this form, where we have the real and imaginary part of the temperature in the frequency domain. So it will be the system which will be analyzed. So it is the FinFET. So we have the 4 transistors with 4 channels. We have the source and drain for each transistor, and we have gate which will be used for controlling of this. And after simulation, we'll obtain the following results. So as you see, for the 1 gigahertz, we have delay described by TQ minus TT. And for 10 gigahertz, we have these results, this delay. And of course, we have the smaller amplitude for 10 gigahertz. Okay. For this simulation, we have to use also the temperature. The temperature can be calculated using scalable model of the FinFETs. And in this purpose, I will use the Fourier transform in the limit sense to approximate the power dissipated in the transistors. So there are final results for the FinFET. There are results for the GAFET, VASFET, and two-dimensional model of the FinFET. So this again, GASFET, VASFET, and FinFET. And as you see, in case of the FinFET, in case of the Fourier-Kirchhoff, we have overestimated temperature. In case of the DPL, typically we have lower temperature. It is temperature approximated in this cross-section of the channel. Okay, now we will go to the test board, which was designed and developed for check and for validate the model and for estimate the parameters, thermal parameters of the integrated circuit. So as you see, we have the signal, input signal and output signal is in this on these connectors. We have transmission lines, and we have the integrated circuit in this place, and you have bonding using wires to this integrated circuit. So in case of the electric domain, we'll mainly consider the transmission lines, which each of them can be described by this equation, but generally we will use 2 waves, and generally we will say about the power which is incident, power which will be reflected, and power which is transmitted by this line for higher frequencies, for example, 100s of megahertz, 300s of megahertz, 1 gigahertz, and more. And now we will use the scattering parameters. So in case of the description of the transmission lines, we'll use these parameters instead of the voltage and current. And we will use the S parameters or scattering parameters described by this matrix. So we perform several measurements in which we will analyze the parameters of the PCB. Based on this, we will calculate the the theoretical and fitted model of the transmission line. After that, we try to use the testing board dedicated to this experiment. So the power is supplied on these connectors and is obtained by these ones. The electric signal will go to this place, will return. And in this place, we have the two resistors. The first one, which have red color, is used as a heater, and second one resistor, which have yellow color, is used as a temperature sensor. So using this structure, we'll try to obtain parameters for DPL model, and so the part of the electrical energy will go in this direction. From this energy, the part is reflected, and second part will go to the thermal domain. In the thermal domain, we'll use the DPL model, which will describe changing of the temperatures, and the changing of the temperatures will be obtained, will be analyzed from the electrical domain, will be transported to the electrical domain, and using this resistor, we will analyze it outside of the circuit. Using the analytical and numerical model of this system, we can find that one of the best places to analyze the DPL thermal parameters are for 150 megahertz in electrical domain and 300 megahertz in the thermal domain. So using the model of this thermal system, we'll find that for different parameters of the TH, so it is the delay for temperature gradient, we'll obtain different results. And this set of the results is associated with the argument of the upper resistor temperature. So finally, we will obtain the results, and from the S21 arguments of the scattering parameter, so S21, it means that it is parameter which is connected with the transfer energy from the electric input to the thermal domain. We can calculate the final T-tau, it is final delay in the for the temperature domain, and as you see, we will obtain 61 from the theoretical analysis. Previously, we calculate that we should use about 60 nanometers. So we have very good agree with previous analysis. And we have the experimental calculation of these parameters, so we are sure that we can use it for regular circuits. And this method is useful because we can calculate the numerical, we can estimate the thermal parameters for any technology of which is used for fabrication integrated circuits.
I'm so sorry.
Okay.
So we have schedule, so I'm so sorry. Can you please move to conclusion?
So I will conclude. So we propose a method which can be used for estimation of the thermal parameters of DPL model. We obtain the results which are similar to the previous analysis. And we can use this approach for modeling more complicated system and modern processors and modern MEMS systems. Thank you very much.
Thank you very much. Thank you so much for very nice, informative talk. Maybe we have 1 minute for very short question. So, do we have any questions?
Can I have one question, please?
Yes.
Yeah, so thank you for a very nice presentation. So it was very interesting that you have introduced imaginary time, right? Am I correct, Professor Zubert?
No, imaginary temperature.
Imaginary temperature.
And of course frequency, but in the Fourier we have also imaginary.
Why I'm asking, because in quantum physics you have Keldysh contour, so you have imaginary time that is translated to inverse of temperature, but you have quite oppositely, so you have like imaginary temperature translated to time. So somehow this analogy might be somehow exploited in a deeper way. So that's the first thing. And second thing, did you analyze the speed of phonons propagation across your structures? Phonons.
Yes, in case of, so thank you. I have imaginary part of the time. In case of the phonons, we have the, in this place. Typically, the length of the path of the phonons is from 30 nanometers up to 130, 170 nanometers. But this size is larger than the typical size of the modern transistor. So it is one of the reasons why we cannot use traditional Fourier-Kirchhoff model. And in case of the more complicated geometry of the system, we can obtain, maybe we will obtain problems.
I see. It's like phonons, the difficult mechanism of phonon scattering, something like that, right?
Yes.
That is captured by your mathematical formalism on a phenomenological level, right?
Yes.
Okay,
Yes.
thank you so much.
Thank you.
Thank you once more again for very nice talk. So I close this session. Thank you.
Thank you very much.